in a good position to take a few minutes. You can rest your hand here for a minute, because I know it's a lot of drawing. We'll go away from the carbohydrates. We'll take a few minutes to start thinking about, this is material in Chapter 20, and dealing with some nitrogen nucleophiles. And a few new things, but also still paralleling a lot of the chemistry of aldehydes and ketones that we've seen. And I know this is where it kind of gets exhausting with the summer course, that we covered a lot of material and we're just going to keep on going. So we will cover a little bit of this today and the next time as well, and then spend time tomorrow reviewing and recapping for our exam that's coming up. So hopefully you've had a chance to watch, again, another Emmy-winning video about the nitrogen nucleophiles, and one thing in particular about the pH dependence, which is really important, and I think sometimes confusing at first. But let's look here at the mechanism as a starting point again. And you may have noticed here, as much as possible in our class, at least the way I like to present it, I'm not saying this is good or bad, it just seems like a way of doing it, is that you have an observation. So this is what we do with the glycoside. So now let's say our observation is we take this ketone, acetone here, we react this with the primary amine, which is making this a generic amine with R, NH2, and a bit of generic acid, like maybe sulfuric acid and water. And you end up forming this functional group here, this imine. And you have a way of figuring that out. So what I like to do is that we come up with an observation. So I've turned A into B, and now we want to figure out what's an explanation for that. And the reason for doing that is, one, is it hopefully makes it kind of interesting. And then two, this is actually how science works. And then I'll get you a question here in a second, Pauline. And then, however, if you take now this same ketone, I'm not sure why I didn't put this one in the box here. But instead, we react this ketone now with a secondary amine with two R groups. Now we're going to end up instead with this structure here, which is an enamine. So now we no longer have a carbon-nitrogen double bond, but instead we have a carbon-carbon double bond here. An alkene here, alkene amine, or an enamine, or an enamine, as some people might say. So we want to figure out what sort of a mechanism can we use to not only describe the formation of one of these species, but why is it that we get this difference with the primary amine, one alkyl group, two hydrogens, versus a secondary amine, two alkyl groups, one hydrogen. So hopefully everyone's curious now about this mystery that we have. And before we get to that, just to hold the suspension, the exam will go up into Chapter 20, which is what this material is. It's not going to cover all of 20, and I'll mark where where we're going to stop in Chapter 20. The reason I haven't done it yet is because I don't know. It depends on how far we get today, and just with that little bit of tomorrow. But I'll have an idea here in the next 20 minutes where we end up today. So at least up into a little bit of Chapter 20. So then let's figure out this mechanism for this imine formation and see if some of the material that we've already covered can actually come up with a way of explaining that. So let's start with our acetone that we'll use. And why don't we just use methylamine, this compound here. Another hydrogen. Even though I don't think you can buy this one. It's used in making methamphetamine, I think. So, but we'll use it on paper. It's fine. So this methylamine here, this is where something is a little bit different than what we've seen before. But let's just assert for a minute that this is going to attack here, just like what we've seen with a variety of other nucleophiles, and move electrons up onto this oxygen. So let's see what that gives us. So that's going to give us a species now where we have the oxygen. I'll come back to that in a second. Nitrogen, two hydrogens. Now we need to account for our formal charges. Yeah, Breaking Bad, they use methylamine. Somehow, I think we have this in our lab. I got it from a long time ago. But So we're going to now deal with the formal charges. And so this nitrogen now has a positive formal charge. And in this particular case, I'll draw on lone pairs of electrons. So we start off with 2 lone pairs of electrons on the oxygen. Oh, sorry. And we still have those 2 lone pairs of electrons. Plus, we've had a pair of electrons from this carbonyl double bond. The carbonyl group move up onto this oxygen. So now this oxygen has a negative formal charge. So we have this dipolar intermediate. I'm kind of taking us through this in a painstaking way is because unlike the reactions we saw with oxygen nucleophiles, remember under acidic conditions, like we have up here on the top with a little bit of acid, we said, when in doubt, always protonate the carbonyl group under acidic conditions. Although this time we actually didn't. Now, it's for a couple of reasons. One is that we're going to see hopefully today, is that we have actually much less acid in these reactions than we would in the case with the oxygen nucleophiles. So it's less likely that this carbonyl group is going to be protonated. That's a very subtle observation. 2 is that the nitrogen species, the amine, is a better nucleophile than our oxygen nucleophiles, so you don't necessarily have to protonate the carbonyl group for this to attack. Now, if you're looking at your other favorite organic chemistry textbook, it may actually show this carbonyl group protonated first, and in reality, it's probably a combination of lots of different things. Sometimes this is attacking with the group protonated, sometimes not being protonated, which I'm showing here. So I don't want us to get too bogged down into those details, but this is probably the predominant mechanism. Okay, so don't worry so much about that. Whereas this looks a little bit different in terms of the protonation state. This is probably what's happening most of the time, but at other times this group may be protonated a little bit. But let's go forward. So now what we're going to do in order to form our imine here on the top, this carbon-nitrogen double bond, thinking ahead, we probably will want to turn this O- here into a good leaving group so that then somehow this nitrogen maybe could kick it out just like what we saw with our acetal. So we need to undergo a couple of proton transfer steps. So why don't we first have it, I'm not sure which one is going to happen first. Let's go ahead and have water, just say take off one of these protons. This is still O-. Now we have a neutral amine, a little bit of H3O+. Let's go ahead and have this O- get protonated. So now we have this neutral species. So now we have an amino alcohol. So see, that's buried down in there. Now we're pretty much just one step away from having a good leaving group here. We still have OH, and so if this was the leave, it would leave as hydroxide, OH-, which is unfavorable, but we have, let's say, a little bit of acid around, as we mentioned earlier. Let's go ahead and protonate this group. Go down. So now this looks very similar to our oxygen nucleophile cases with the acetal. So we have a good leaving group. So let's highlight that here. Good leaving group. And so now we can use our lone pair of electrons on the nitrogen to kick that group out. So we've lost water. And we have this species here. This is known as an iminium ion. And now all we have to do to generate our final product is have, say, water come in and take off that last proton. go down below a little bit here. And we would form this, plus H3O plus. So that's our formation of an amine from a ketone. So we started off with a ketone. In this case, it could be a ketone or an aldehyde. Reacted it with, let's put it here, our primary amine. Just happened to use methylamine because it's easier to draw. And we ended up with an amine, or an imine. Amine, or amine, as some people say, and imine sound very similar. I've heard people say imine, but I think it's true imine. So now, what's happening here overall is we had this little bit more complicated acid-base chemistry first step that we mentioned, that the nitrogen nucleophiles were asserting is nucleophilic enough in the presence of only a small amount of acid to attack the carbonyl carbon, generates this dipolar intermediate. Now, the next several steps are all proton transfers. So we're taking a proton off the nitrogen, we're putting a proton on the O-, we're putting a second proton on the O-, now to generate this neutral amino alcohol first. I'm sorry, I misspoke. We first put one proton on to generate the neutral amino alcohol. Now, what we're going to do is protonate the second time to turn this into a good leaving group. What's different from before is that we have a nitrogen here as opposed to an oxygen. But mechanistically, it's the same idea. Turn a bad leaving group to a good leaving group below, kick that leaving group out, now using a nitrogen, lone pair of electrons on the nitrogen in place of oxygen, generates our iminium ion. And then in the last step, we're going to deprotonate to generate our final imine. So very similar to what we've seen previously, but there are differences.